Engineers often hit invisible walls inside their own machines, security protocols that abruptly slam shut on their code. You spin up a local development environment and write a standard script to pull data from a private backend API that you control. If you execute that request through a terminal using curl, the data returns immediately. The connection is clear. But if you write the exact same request via a JavaScript fetch command in the browser, the data is quarantined before it reaches your application. You open the developer console and see a familiar error, blocked by CORS policy. When we see this error, we often assume the backend server rejected an unauthorized request to protect its data. In reality, the server likely processed your logic and successfully returned the payload. The blockade happens on the return trip. Your browser intercepted the server's response and destroyed the data before the JavaScript runtime could access it. Effectively debugging this requires recognizing that the server's job ended when it sent the response. The browser is the only entity deciding if your code is allowed to see the result. This quarantine is driven by the same origin policy, the foundational rule governing how browsers handle traffic. To the browser, an origin is defined by three components: protocol, host, and port. Imagine a React frontend on port 3000 trying to talk to an Express backend on port 5000. Because the ports differ, the browser identifies a mismatch and severs the connection. Unless two scripts share the exact same protocol, host, and port, the same origin policy forbids them from reading each other's data. The browser isolates every origin, treating external scripts as potential threats by default. This isolation exists to address a specific vulnerability in how browsers handle user sessions. Consider a user who is securely logged into their banking portal in one browser tab. In a separate tab, that same user visits a compromised website. Browsers use ambient credentials, automatically attaching saved session cookies to outgoing requests for recognized domains. If a malicious tab sends a fetch request to your bank's API, your banking session cookies are attached as the request leaves the browser. The bank server sees a request with valid cookies and returns your sensitive financial data. The browser gatekeeper intervenes here. As the data arrives, the browser recognizes the origin mismatch and destroys the payload. The same origin policy acts as a shield for your session data, preventing malicious scripts from accessing information that was never intended for them. Cross-origin resource sharing is the standardized mechanism for punching a controlled hole through this isolation. When you make a cross-origin request, the browser injects an origin header, telling the server exactly where the script is running. The server processes the request as it would any other. If the server wants to permit the read, it must attach a permission slip to the response, the access control allow origin header. When the payload returns, the browser network layer holds it in a sandbox, keeping it away from your JavaScript. The browser then compares the original origin it sent against the allow origin header provided by the server. If the headers do not align, the payload is permanently quarantined and your code receives a type error. If they match, the sandbox opens and the data resolves in your code. The server provides the permission, but the browser handles the enforcement. This explains why local proxy servers in tools like Vite effectively bypass CORS errors. Instead of calling the backend directly, the frontend sends the request to the local proxy, which then forwards it to the API. This communication is server to server. Since no browser is involved in this leg, the same origin policy never applies. The proxy then sends the data back to the frontend. Because the proxy and the client share an identical origin, the browser's security check passes. Proxies structurally bypass the browser's security sandbox, proving that CORS is strictly a browser-level construct. Because the server processes requests before the browser evaluates CORS headers, there is a significant security gap. This is particularly dangerous for state-changing operations like post or delete requests. If a malicious site tricks a browser into sending a cross-origin delete request, the server will execute that action. The browser will block your code from reading the success message, but the data on the server is already gone. CORS restricts the reading of data, but it cannot prevent the execution of logic. Protecting the backend itself requires independent defenses, such as anti-CSRF tokens or strict same-site cookie attributes. CORS secures the user's data within the browser environment. Safeguarding the server remains the developer's responsibility through dedicated backend architectural defenses.